Hello everybody, welcome to this short webinar on demystifying C++ lambdas. Now, lambda expressions are a feature that many programming languages have had for many years, but they were added to C++ in the major update of 2011, and they've become somewhat poster child for modern C++. What we're going to do in this session is have a look at the syntax and the semantics behind C++ lambdas, and also beyond that into the idea of callable objects and the standard function from the standard library. To start off with then, let's start with some simple context examples. What I have here is a simple abstract data type, my class ADT. It's got a couple of methods on it, op and getValue, and I'm storing those objects in a vector. I've just inserted some objects, so I've got something to process. And in this particular example, I've handcrafted an iteration through the container where I'm starting at the beginning, iterating through to the end of the container, and I'm calling the getValue object method on every object I find in the container. Now, there's nothing wrong with this code. It works perfectly well, but it's not the preferred way of solving the problem. C++ core guidelines prefer that we should use standard library algorithms wherever possible. The algorithm I've chosen here is the for each algorithm that iterates through a range derived from two pointers or iterators. In this case, I've set the beginning of the range to be the beginning of the vector v, and the end of the range I'm using the call to end. In this particular case, I'm using the helper functions that are provided with the standard library. Now, there's a problem with for each, and the problem is that it can't directly access member functions on a class. There are several ways to solve this, but in this particular case, I've hand-coded a function called process. Process takes an ADT object and then calls it getValue method. The call to process is passed in to the call to the for each algorithm. Technically, what I really should be doing is using a functor. A functor gives me more flexibility. What's a functor? You can think of a functor as a function with its own independent state, or perhaps more pragmatically, as any class that implements the function call operator, sometimes called operator parentheses or operator parens. I've highlighted it here on the code. What this allows me to do is to create an instance of the functor class, and then I can call that like a function. So I can pass my functor object into the for each algorithm. What have I gained here? Well, very little actually. What is happening, however, is I'm cluttering up my code with extra class declarations just so that I can call a simple member function on one of my working classes. And this is where lambdas come in. A lambda expression is an ad hoc functor object. Now, a little bit of terminology here. What you see on the screen at the moment is a lambda expression. This is what you type into your code. A lambda expression is used by the compiler to generate what is known as a closure object. Now, a closure object must have a type, and in C++ parlance, the type of a closure is called its closure type. So here's the syntax. The brackets here define the start of the lambda. You can think of it as an unnamed function in this case. The brackets also act as what is called the capture list. We'll return to that shortly. The function can have as many parameters as you like, and it can have a non-void return type. In this case, we have to use what is known as trailing return type syntax. And then finally, the lambda has a body, and this is just C++ code. There's a few things we can add to this, or rather remove. If the lambda requires no parameters, we can leave off the parameter list. If the lambda returns a void return type, we can leave off the return type, and we can also leave that off if the compiler can deduce the return type from the body of the lambda. In this case, it would be able to deduce that the return type is in fact an integer. So we can actually reduce the amount of syntax we type in. What does this give us? Well, let's take an example. It gives us something that we haven't hitherto had in C++. This is the idea of a block-scoped function. In C++, functions can be in global scope, they can be in namespaces, or they can be given static scope, that is, limited to within one file. Lambdas give us another extension to this, which is the idea of a block-scoped function. That is, a function that can only be called within the scope within which it is defined. I've done that here. I've written my lambda expression, and I've created an object, a closure object called lambda in this particular case. And notice I've used automatic type deduction. I have to in this particular case because the type of the closure that is created is only known to the compiler. I can't possibly know what it is. So therefore I have to let the compiler automatically deduce that type for me. Once I've created my closure object, it's a functor, and I can call it just like a normal function. So in this particular case, I'm calling it once with the value 100. However, please note that function is not accessible anywhere outside of func. So for example, in main, I can't call my functor lambda. It's not in scope anymore. Let's apply this to our previous problem. Here's my code from previously, but now instead of creating a functor, I'm using a lambda expression to get the compiler to generate that functor for me. What I can now do is substitute in the lambda closure object in the call to the for-each function. This is better, but I can do even better still. In the case of the for-each algorithm, I only need the functor's behavior in the algorithm. So what I can do is actually substitute in the lambda expression for its object. Remember, the lambda expression automatically generates a closure object. So now what will happen when the code runs is my closure object will be generated, my iterators will be evaluated, and then the call to for each will happen. In this particular case, what will happen is my lambda closure will be passed each ADT object in turn, and then it can call its function. This has now reduced the processing I need just down to where I need it. I no longer need to clutter up my code with extra functors or extra function calls that are not needed anywhere else. Let's have a look at what's happening under the hood here. Here is my lambda expression that I type in. What is the compiler generating from this? Well, conceptually, it's creating a class of some generated name. We don't know what that is. And it's implementing it as a functor. So it's implementing the call operator. Notice the call operator parameters are the ones I provide in the lambda expression, and the body of the call operator is the body of my lambda expression. Notice also that this call operator is marked as a const function. That is, inside the body of the call operator, I cannot modify any of the objects. They're all const objects. Now I've marked this as conceptual because in reality the compiler doesn't actually generate this new type. It will probably go straight to abstract syntax. Here's my client code again with the call to for each and my lambda expression as the third parameter. What the compiler is doing is conceptually adding in my new type, my lambda type, my closure type, and then creating an instance of that object just before the call to for each. To be a true closure, we also have to be able to capture the context for the closure. What does that mean? Well, it means grant access to objects outside the scope of the closure, known as the context. In this particular case, we can capture anything that is currently in scope. We've only got one object in scope in this case, that's the variable I. Notice I've added the name of that object into the capture list of the lambda. By default, captures are made by value. That is, a copy of I is made inside the body of the lambda expression, not the original object. So the original I object cannot be modified in this particular case. Now that may not be desirable for us. Perhaps we do want to modify the object. So what we can do is actually capture objects by reference. In this particular case, the lambda captures the total object by reference, and now I can update the total. Please note, a reference to the object is stored. It is the reference that is constant, not the thing that the reference refers to. So I can actually modify total from within the body of this lambda expression. That will work. The language also provides what are known as default capture modes. I can capture everything by reference by using the ampersand. I can capture everything in context by value using the assignment operator. Now, on the face of it, this does seem like it's going to be extraordinarily inefficient, bearing in mind the types of objects I have currently in my context, like my vector of 1,000 doubles. The compiler is free, however, to optimize away any objects that are not referred to inside the body of the Lambda. So it only captures things that are actually going to be referred to. Still, that said, that is an optimization. General good practice says, if you can avoid it, don't use the default capture initializers. Be explicit when you use them. What's going on under the hood here? How does capturing the context work? Well, quite straightforwardly, when I write my Lambda expression, the compiler, again, conceptually generates the following code. It adds a constructor to my closure type, and internally, it stores attributes, which is the reference to total and a copy of the offset. I've shown these with the names total underscore and offset underscore. We don't know what their names are. Notice the constructor initializes those objects. This answers a very common question in Lambda expressions with capturing the context. That is, when does the capture actually happen? Well, knowing how the Lambda and the closure type are generated, it's relatively easy to see now when the capture occurs. The capture occurs when the closure object is created. In our case, it happens just before the call to the for each algorithm. Some other things we need to know about capturing context. In this particular example, we have a class filter with an operation called filter on it. Internally, we are using a standard algorithm, remove if, and as the predicate on this algorithm, we are using a Lambda expression. In this particular case, we are going to remove any elements from the container V that are less than some attribute level. Now, at the moment, that code won't compile because the Lambda expression won't know anything about the variable level in this case. To grant access to that member variable, we have to capture this pointer on the class by value. There may be some times, though, when capturing by reference or capturing by value may not be desirable. Let's take an example. One of the things about Lambdas is they generate closure objects. The closure object could have a lifetime longer than the elements it actually references. This could be a problem. We could end up with dangling references in our code. How we do that, I'll come to later on, but let's assume that we can do it for the moment. And the Lambda expression generates an object, a closure that could exist longer than the scope of the object it's capturing in its context. So I don't want to capture by reference. And in this particular case, a very contrived example, I can't capture by copy. In this case, I'm using a unique pointer to store the results of some processing. Why? Because I need something that can't be copied. What am I going to do now? I'm going to call the function doStuff. DoStuff is a template function. Its template parameter is expecting a function-like object as a parameter. And what it's going to do is execute that function-like object. We've called it run this. In our example, the function-like object that we're going to pass is our Lambda expression. Now, this won't compile because we don't want to capture by reference and we can't copy a unique pointer. Now, this was a problem in C++11. There are workarounds for it, but in C++14, they added in some extra syntax that allow us to solve this problem. What we can use is what is known as a capture initializer. In the simplest case, a capture initializer is an alternative name for an object captured in the current context. But a bit more than that, the capture initializer has two parts. First of all is the local name, and that can be any name you want. The second part, and the most important part as far as we're concerned, is the right-hand side of the initializer, and that is an initialization expression. And that expression can be anything you want, as long as it yields an object of the correct type. So in this case, what we are doing is initializing the Lambda local name, res_pointer, by moving result into the Lambda expression. What's going on under the hood here? Well, there is my Lambda expression. Here is the compiler generated code. Again, conceptual. We are storing the unique pointer internally because we're capturing by value, but because we can't copy it, the initialization expression is used in the constructor of my closure type and is used to pass in the object to res pointer. That solves our problem. Here's another example to help us explore some more of the syntax of Lambda expressions. At the top of the screen here, I have a function called process. It is a template function, perhaps from some library. It is expecting a template parameter of some container type. That is, it is expecting a container as its parameter. We just don't know what sort of container it is. Inside the code, we're going to iterate through the container and output each element, a trivial piece of code. There is a bit of a problem with this. The for each algorithm is expecting an object of a particular type. It is not expecting a container. So what I've done is here said the parameter for the Lambda expression in this case is whatever the value type on the container that we've passed in. Now that places a restriction on this process function. That is, whatever template parameter container type we provide, it must support the value type alias. So if we call process down at the bottom here with a vector, that will work. Vectors support the alias value type. However, if I call the function with a raw C-style array, that won't work. When the compiler deduces what the type of array is, it will work out that it in fact is a pointer to an integer. It will degenerate the array to a pointer. And pointers to integers do not support the alias value type. Therefore, our code won't compile, and we'll get some horrendous error message. The solution pre-2011 involved generating type trait classes and was generally a lot of code to solve the problem. In C++ 14, however, they gave us the concept of a generic lambda. Generic lambdas are for solving exactly this sort of problem. In this case, the parameter that is passed to the lambda in the process function is marked as auto, which is a clue to the compiler saying, please deduce what the parameter type is from its call. Now my code will work with vectors. It will also work perfectly well with raw arrays as well. So how is this working? Let's look under the hood once more. Here is my generic lambda. The compiler, as we know, will generate a class in this particular case. The difference is now when I mark my generic lambda as an auto parameter, the compiler now generates the call operator as a template function. And now it will use template type deduction rules to work out what the type of T is from the call to the call operator. That's all that's happening. Lambdas now fall into a set which in modern C++ are known as callable objects. Callable objects are any objects in the system that can be called like a function. So obviously functions are callable objects because they can definitely be called like functions. Member functions can be called. Lambdas, as we've seen, can be called like functions, and so can functors. There is a problem in C++ that isn't the case in C. If we look at C code, pointers are quite straightforward. You can have a pointer to an object, and the type of the object and the type of the pointer must match. Or you can have a pointer to a function, and the function signature and the signature of the pointer must match. However, in C++, the signature for a member function is going to be very different to the signature for a free function. And it's going to be different to a functor. And in the case of a lambda, we can't possibly know what the closure type is of the lambda. So it's very difficult for us to declare a pointer to that function. So what we need is some generic mechanism where we can have a generalized pointer to callable object. And in the standard library, that's what standard function is. It's a callable object wrapper. You can think of standard function as being like a generic pointer to a callable object. Standard function has a template parameter, which is the signature of the function that is going to be called. So it will have a list of parameters and it will have a return type. Any callable object that matches or can degenerate to that signature can be stored inside a standard function object. Let's take an example of this. Here I've built a very simple class called simple callback. Internally, it stores one attribute called callback of type standard function. Notice the signature of standard function. It can be bound against any void callable object. That is, a callable object that takes no parameters and returns nothing. If you like, you can think of it as just a pointer to a function of that type. We're going to initialize that standard function in the constructor of simple callback. In the function execute, we're going to call that function. Now, because standard function acts like a generic pointer to function, we can also compare the callback to null pointer. That is, has this standard function actually been given the address of a callable object? The real strength of this is now I can create a simple callback with a functor. The call operator on my functor class here is a void function that takes no parameters. And when I call execute, that parameter will be executed. I could call it with a simple function. And because Lambda expressions also form callable objects, I can call it with a Lambda expression as well. The really powerful thing about standard function is it's an object, it can be stored in a container. So I can now have a container of standard functions and I can initialize it with any callable object. And those objects could exist long past the definition of the original entities. This is why capturing by reference is a potentially dangerous thing to do. If I have my simple callback and it is initialized with a Lambda expression, and that Lambda expression captures the local context, that local context may not be valid when the callback is finally executed. So be careful with this. If we're talking about standard function, we should also talk about standard function adaptation as well. Here we have a callable object that has 3 arguments. This may not be usable in our code. Let's take an example. If I am using callable objects inside a standard algorithm, they may only be able to pass 1 parameter. So what we need is some way of changing the signature of my callable object into something that is usable for me. And this is where standard bind comes in. Standard bind takes a callable object as its first parameter, and then it allows you to bind either absolute values to arguments on the callable object or expose arguments to the outside world. The way we expose arguments is using these placeholder elements, placeholders _1, placeholders _2. Placeholders is a namespace. The placeholder number _1 or _2 defines which parameter it will be in the output standard function that standard bind generates. So placeholders _1 will be the first argument, placeholders _2 will be the second argument. What standard bind will do then is create a new function object where either parameters are passed on to the callable object internally or hard-coded values are bound to arguments. Let's take an example of this. Here we have some generic class X and it has 2 functions. One called oneParam, which, as the name suggests, takes a single parameter. One called twoParam that takes 2 parameters. Strictly, that's not true. The method oneParam actually takes 2 parameters. It takes the integer, but it also takes the this pointer as well, the address of the object. Similarly, twoParam takes 3 parameters, the this pointer plus the 2 integers. If I want to call those methods in a standard algorithm, I might do something like this. Here is my vector v of x objects, and I'm going to insert some objects. My for each algorithm takes a range. I'm going to iterate through the entire range of the container. And what I want to do is call the oneParam method. This is a problem because oneParam actually takes 2 parameters. The address of the object, which the for each algorithm can supply, and also an integer parameter, which the for each algorithm cannot provide. So I'm going to use standard bind here. For the object, I'm going to use placeholders _1, and that will be the actual object. For the second parameter, the int I, I'm going to hard code and bind the value 100. Similarly, on the second line, I'm going to call toParam method, and I'm going to pass placeholders _1 as the object, and I'm going to hard code the two separate parameters 100 and 200. This works absolutely fine. Of course, if you think about it, we could also use a Lambda expression and capture context at this point and do that instead. That would also work perfectly well and is generally the preferred option. One, it is more explicit, and two, it is quite often a lot more efficient to do so. But while we're talking about standard functions and function adapters, it would be remiss of me not to mention standard bind and how it could be used. For those of you familiar with C++ 03, standard bind now replaces bind first and bind second. So this is a very brief introduction into the wonderful world of Lambda expressions. The key thing to take away, Lambda expressions are syntactic sugar to allow the compiler to generate ad hoc functor objects, functional objects. The real strength of that is it gives us a new feature in C++, the idea of a block-scoped function or block-scoped functor. This allows us to capture our processing code as close to where it's going to be needed as possible. Taking that idea on into the idea of callable objects, we now have standard function as well, which acts as a generic pointer to function or pointer to callable object, which can be stored in containers and used to process as well. There's a very brief introduction there to Lambda expressions. Hopefully that's been useful. Hopefully it's cleared up a few points of confusion you may have had. If you want to know more, please come and visit us on the blog at www.feabhas.com. And to summarize up, thank you very much.